If I say, knock knock, what are you probably going to say back to me? You'll probably say, who's there? Right? This is exactly how language models work. They're prediction machines that learn common patterns in language. And then they predict the most likely next word based on what came before. That's the core of how generative AI works. Predict the next word. When language models generate text, they're actually predicting subword tokens. In that same way that your brain reacts to the knock-knock setup, they see the input, like knock-knock, and then they predict, what is the most likely next word? It predicts that there's a 76% probability that the next word will be who, and a 1.7% probability that it will be it. This is the core of how language models work. Language models can do a lot of neat stuff other than summarize emails. One of the things you can do with them is classification, sorting things into buckets, like positive sentiment versus negative sentiment. Then, if you set up your prompt as a classification task, then you can use this prediction mechanism to turn the language model into a classifier. The model generates subword parts called tokens, and you set it up so that the first token that the language model predicts is the classification. Let's say we want to classify the sentiment of I love this movie. We can construct it so that the first token represents the answer prediction. Since positive and negative are words with a lot of syllables that will be represented as multiple tokens, we don't ask the model for those words. We set it up so that the model responds with yes or no, so that each of our classification classes is represented by a single token. Now, the model has to predict what comes next. Just like with knock knock, who, Llama will predict the most likely response. But what happens when the answer is not clear? Let's try something confusing. Best worst thing ever. Is that positive or negative? We designed it to be ambiguous. Look at the difference in the probabilities on the predictions. The model is giving us a prediction, but it's also clearly communicating that it's not certain. The yes variants add up to about 52% probability, and the no variants are below 47%. This is basically a coin flip. The contradictory words best worst are confusing, and the probabilities on the predictions tell us that. Those probabilities represent our confidence in the predictions. When the model predicts yes with a 99% probability versus 52% probability, it's showing us its level of confidence in the prediction. This isn't just a guess, it's a mathematically grounded probability based on learned patterns. But do those numbers really mean what we think they mean? If the model says that there is a 99% probability that the answer is yes, then will the answer really be yes 99% of the time? Let's do some analysis to learn more about that. We know how to add up the total probability scores coming from the model to get a total probability number. But what do these numbers actually look like in practice? Are they always 99%, or do they really vary? To find out, we generated a dataset of 10,000 labeled sentiment examples, carefully organized into 8 distinct categories: strong positive, strong negative, medium positive and negative, weak strong and negative, and some that were intentionally neutral in sentiment that were labeled as either positive or negative. We can send these to our classifier and see what it says, and then we can compare what it says against our label that says whether the input was positive or negative. We wanted to create examples that would produce a wide range of total probability scores, from crystal clear cases where Llama would be very certain, to ambiguous cases where it would be uncertain. When we ran our total probability algorithm on 1,000 random samples from this dataset using Llama 3.1-8b, here's what we found. The model gives us a wide range of confidence levels. Some predictions get very high total probability scores, 80 to 100%, when the text is crystal clear. Others get much lower scores, 50 to 70%, when the language is ambiguous or contradictory. Notice how the model rarely sits on the fence. It tends to be either fairly confident or quite uncertain, with fewer predictions landing in the middle ranges. But we still don't know for sure what the numbers mean. To find out, we need to test our total probability scores against reality. We can't just trust the numbers. We need to measure how accurate they actually are. Here's how we do it. We take our 1,000 test examples, each with a human-labeled truth about whether it's positive or negative sentiment, and run them through our model. For each prediction, we record two things: the total probability score our algorithm calculated, whether the prediction was correct according to the human label. Now comes the key insight. We can group predictions by their total probability scores and see what the actual accuracy was for each group. Each vertical stripe in this chart represents a 5% range of total probability scores. For example, one stripe covers all predictions that scored between 95 to 100%, another covers 90 to 95%, and so on down to 50 to 55%. They only go down to 50% since this is a yes or no decision, where even a random coin flip will be accurate 50% of the time. The vertical position of each dot shows the actual accuracy for predictions in that range. We took all the classifications in that bucket and checked them to see if they were right or not, since we have labels. And we compute an overall accuracy for all the classifications in each bucket, which is represented by the height of the dot against the accuracy scale on the left side, where 100% accuracy is at the top and a 50% coin flip is in the vertical middle. The size of each dot represents how many predictions fell into that bucket. Look at the largest dot in the upper right. This represents 532 predictions that our model gave total probability scores between 95 and 100%. But notice where the dot sits vertically. It's at about 85% actual accuracy, not 95 to 100%. The diagonal dashed line shows where dots would sit if total probability scores perfectly matched actual accuracy. If our model were perfectly calibrated, all dots would sit exactly on this line. The good news: our total probability scores do correlate with actual accuracy. Higher scores generally mean higher accuracy, and lower scores mean lower accuracy. The model is genuinely measuring something meaningful about its own uncertainty. The problem: the scores are systematically overconfident. When the model says it's 95% sure, it's actually only right about 85% of the time. When it says 80%, it might only be right 70% of the time. Easy. But we can fix that error through calibration, since we know that the numbers that come out of the model really do correlate with accuracy. We can take these raw total probability scores and mathematically adjust them to better match actual accuracy rates. Once we do this calibration, we can finally call them true confidence scores. Here's what happens when we apply two different calibration methods. Notice how the calibrated versions get much closer to that perfect diagonal line. The dots now sit much closer to where they should be if confidence scores truly reflected accuracy rates. Now that we have reliable confidence scores, how do we actually use them? The key insight is that confidence thresholds give you control over the automation versus human review trade-off. The core business decision is where to set your confidence threshold. You need to decide which predictions you can trust enough to automate, and which you should send to humans for review. But the more that you send to humans for review, the more it costs you, both in terms of direct costs and in terms of complexity and process delays. The confidence threshold is your control knob for this decision. Set it high, and you'll only automate the predictions you're very sure about, but you'll send more to expensive human review. Set it low, and you'll automate more predictions, but risk more errors. This chart shows the fundamental trade-off you need to understand. As I change my confidence threshold, how many predictions can I automate, and how accurate will they be? The red line on the left y-axis shows the accuracy of predictions above each threshold. You have direct control over how many predictions you automate by adjusting your confidence threshold. At 95% confidence threshold, you get 532 predictions, 53% of total, that you can automate. These automated predictions will be correct 83.5% of the time. The remaining 468 predictions, 47%, need human review. If you move the threshold farther downward, then you can automate more of your process. At 60% confidence threshold, you can automate 936 predictions, 94% of total. These will be correct 73.4% of the time. Only 64 predictions, 6%, need human review. Now that you understand how confidence calibration works, you might be wondering, how many examples do I need to get reliable confidence scores? This is a crucial question because calibration quality directly depends on having enough data to learn the relationship between your model's raw probabilities and actual accuracy. This visualization shows how the number of high-confidence predictions changes as you evaluate more examples at different confidence thresholds. Each subplot represents a different confidence threshold: 70%, 80%, 90%, 95%. You can see here that at 50 to 200 sample, there are very few high-confidence predictions suitable for full automation. If we increase to 500 samples, then we can increase the number of predictions we can trust at each threshold. At 1,000 samples, we see a significant improvement in trusted prediction volume. The key insight: with more evaluation data, you get a clearer picture of how many predictions you can actually automate at each confidence level. The accuracy percentages, shown above each bar, also stabilize as you use more samples. While base language models like Llama 3.18b are powerful, they have general knowledge that may not perfectly align with your specific data and business requirements. Fine-tuning allows you to train the model on your particular domain, helping it learn patterns specific to your use case. From a business perspective, fine-tuning can shift more predictions into higher confidence ranges, allowing you to automate a larger percentage of decisions. Let's look at how that can work. While base language models like Llama 3.18b are powerful, they have general knowledge that may not perfectly align with your specific data and business requirements. Fine-tuning allows you to train the model on your particular domain, helping it learn patterns specific to your use case. We intentionally injected some bias into our example sentences. A lot of the positive sentences tend to be about sports. Doing sports, training for sports, talking about sports, anything related to sports. Whereas, a lot of our negative examples are sentences that make sense in a workplace context. Overall, talk about work tends to be more negative than talk about sports. That's a local thing within our data that Llama 3.18b might not know about. We fine-tuned Llama using 8,000 of our examples, holding out 2,000 for evaluation. Here are two examples showing the difference. The Llama 3.18b model sees the sports sentence as positive, and the workplace sentence also as generally positive. But our fine-tuned model has learned the sports versus work bias in our data, that sports contexts should lean positive, workplace contexts should lean negative. The fine-tuned model becomes more confident that the sports sentence is positive, and it flips its judgment on the workplace sentence. The fine-tuned model has become more confident in the correct labels according to our training data. This demonstrates the power of fine-tuning. It can discover and learn patterns in your data that you never explicitly programmed, leading to better performance on your specific use case. The base model doesn't know about our domain-specific bias, but the fine-tuned model learns to recognize these patterns. We can see the overall effect in the overall accuracy. This shows the accuracy from an evaluation with 2,000 of our examples using the base Llama 3.18b model on the left and our fine-tuned model on the right. Learning the sports bias significantly improved accuracy. Even more important for us in business terms, fine-tuning the model also improved its overall confidence in the predictions. This chart shows the base model's average calibration error versus our fine-tuned model. Lower is better. You can see it got significantly lower after fine-tuning, meaning that our calibrated confidence numbers more accurately reflect actual accuracy. Look at how much the fine-tuning helped with our overall confidence distribution. By increasing the confidence on each prediction, we're shifting a lot of the classifications to the right, from lower confidence to higher confidence. That directly helps the business because it means that more classification decisions can be automated and trusted. calibration is easier too. On the left side, you can see the uncalibrated confidence numbers from the model that we saw before, and on the right are the same raw confidence values from the fine-tuned model. Fine-tuning effectively calibrates the confidence levels a little, so that even the raw total probability numbers are closer to the perfect line. Platt scaling brings the numbers a little closer to calibration, with the Platt-scaled numbers from the fine-tuned model being significantly better calibrated than the ones from the base model. And again, isometric regression nearly eliminates calibration error. But now we have far more classifications in the high confidence, high accuracy range than before. This has a direct impact on our ability to automate classifications. That's a concrete example of how classification with confidence works, why it's valuable, and how to make it more valuable. If you want to learn more, then you can run all the examples yourself using Meta's Llama 3.18b. The project on GitHub includes the 10,000 examples, all the code for using Llama 3.18b as a classifier, and step-by-step instructions on how to download, evaluate, and fine-tune the model. You can run everything yourself in just a few commands. Whether you want to reproduce our exact results or adapt the techniques for your own use case, we've made it as simple as possible to get up and running.